that I've created called ABCD PyHF. But the package itself is pretty simple. It's pretty small. So I'll spend a decent amount of time explaining all of the other words in my title. And then near the end, I'll actually talk about, once I get through that, then it'll be very easy to show what this package actually does. So should come up in a second here. I'll be talking about this background estimation. That's the main thing, and a particular method for this. It takes too much longer. I can switch to a local one, or I guess I can. Okay, I can start using the static version here. Yeah, so I'll be talking about this package, but first I'll be talking about background estimation in general. The first part of the notebook just ignores some warnings that will go away in some future versions. But here I'll start talking about, so I'm really focusing on analyses that are searching for new physics processes. So, so searches for new physics. And in these analyses, the general idea is usually to look for a potential excess of signal-like events above some expected number of events from background processes. And the expectations of what the signal events look like usually come from Monte Carlo simulation. And in a lot of analyses, they also, the distributions that you expect from background events are also provided by Monte Carlo simulation. But in a lot of searches, it's often impractical or impossible to generate Monte Carlo simulations that accurately model the background that's most relevant in the signal-like regions, and or provide enough statistics in order to be useful for analyses with very low background. And this kind of scenario is especially common, like in the cases that I work on for QCD multi-jet background. And so this necessitates the use of data-driven background models, where the background in the signal region is estimated directly from data that is outside the signal region. And so if, without making any further assumptions about the background, you need at least two independent discriminant variables in order to do this. And so I'll be looking at an artificial example. I don't know why it's taking so long. Maybe I'll try it, because it was already built. But I'll be using kind of an artificial example where I just generated some example data in Monte Carlo. See if it comes up. And you can see that in the there's another notebook in this repository that I use to just generate some fake data and signal. And then I'll just be loading it here. Well, okay, I can switch to the local version.
Sorry, could you please zoom in the font, the screen?
Yeah. As soon as okay, I'm going to stop sharing and then share a different Firefox window. But then I'll do. Binder is unhappy with me. There you go. This is the right one. Yeah. Okay. So now you should be seeing the notebook that I'm just running locally. And yeah, I will zoom in. Let's see. Probably, hopefully, about there is good. Can you see the note? Is this good for the notebook?
Yeah.
That's okay. Nice. Great. Okay. Yeah. So sorry about the binder not working. It worked right before. So let me clear the output first. Okay. Yeah. So I'll load in this. There's a couple CSV files in this repository. So the first one is my fake signal Monte Carlo just generated at random. And so this the signal Monte Carlo, I can actually look at it here in the notebook here. So it's just a bunch of pairs of variables. So I'll call the first variable X and the second one Y, and each row just represents an event. And so these are basically my signal-like events in these two variables. So I can visualize this distribution in signal. So just plotting and just doing a 2D histogram. So it looks something like this. So you can see there's like a peak in the signal distribution, and then it just kind of fades out. The density of signal events fades out as you get further away from this peak in the middle. And so as you'd have in a real analysis, generally you have a relatively high statistics example of what this potential signal should look like in data if it exists. So of course, we don't expect to see anywhere near this many signal events in the real data. It'll be scaled down to a much smaller number of events. And I'll also have to deal with the background distribution of events that this signal is hopefully on top of. So then I'll start looking at distribution of the data. So just loading this other distribution in. So here, again, like in kind of a realistic exotics search, we have a lot fewer data points. So this represents, say, all the events in this plane of X and Y, just a scatter plot of all the events that are actually observed. So the question is, how do we know if there are real signal events in this observed distribution or not? And so in order to answer that, we need a method to estimate how many of these events are from background processes. So here I'm assuming that it's intractable to actually produce Monte Carlo to model this background. We have to derive it from the data itself. So arguably the simplest way for estimating background directly from data is called the ABCD method. And so in this method, you introduce a threshold value in each of the two discriminants that you're looking at, and then separates the plane into 4 regions labeled A, B, C, and D. So here I'm just setting this threshold to 1 in both variables, and then I can just make a plot showing this data distribution with these 4 different regions. So A, B, C, and D. And of course, I've designed this in a particular way, but the statement that follows here is true in general. As long as X and Y are statistically independent, it's easy to show with just some integral manipulation that the number of events in region A is approximately equal to the number of events in B times the number of events in C divided by the number of events in D. And it's only an approximation because of finite statistics. So in the infinite PDF limit, assuming these variables really are independent, this is exactly true. So if these number of events in the regions B, C, and D accurately reflect the number of background events in these regions, this formula gives an unbiased estimator of the number of background events in region A that does not rely on any information from region A itself. So this is the kind of object that we want. So the problem comes from what I show in the next plot. So here, so if I show this distribution and the regions for overlaid on top of the signal Monte Carlo simulation, we can see that, okay, region A is really the most signal-like region, most of the signal events in region A, but there's a significant amount of leakage of the signal events into regions B, C, and D. And so if there really are events that we're observing in data in region A, then there are very likely signal events in data in B, C, and D as well. So this breaks the naive method. If we try to use it, we could totally miss an observation of signal in data. And the results will just be wrong in any case. So the correct and much more robust way to handle this scenario is to use the likelihood-based ABCD method. So in this method, we just set up a system of equations. So there's you have an equation for the number of signal events, or the expected number of signal events in each region. So this is just introducing some variables. So the efficiency of each region normalized to the efficiency of region A. These are all estimated from Monte Carlo, the high statistics Monte Carlo, and then multiplied by mu, which is just a parameter that is allowed to float. It's defined as the number of signal events in data in region A. So this is the parameter of interest, the mu here. This is the signal strength. And then for background, we have the expected number of background events are given by, in each region, are given by these equations here. So there's mu B, which is just a normalization of the number of background events in A. And then you have these nuisance parameters, tau B and tau C. And these are just introduced to enforce the standard ABCD relation. This like NB times NC over ND is equal to NA. So this is always true for the background. It's just in data, we have no way of a priori separating the background events and the signal events, if there really are signal events there. And then with this system of equations, we get the total number of expected number of events in each region is just the signal number plus the background number. And so if we set particular values of all these parameters, we can calculate a Poisson likelihood based on the expected number of events and the observed number of events in each region. And then at this point, we can perform maximum likelihood fits with these parameters in order to do all the statistical tests that you need in order to get your analysis results. So this is where I come up to the ABCD PyHEP package. So this is a Python package that facilitates doing exactly these statistical tests. So it's fairly narrow in scope. This is not like ZFit or iMinui that's doing, or PyHEP itself, which is a very broad and powerful tools. It's specifically a convenient wrapper around PyHEP that allows you to build the proper PDFs and run hypothesis tests for this likelihood-based ABCD method. So first, to just go through how you can use this package. Okay, so I just defined this function so that I can get the yields out from my signal Monte Carlo and data, just to get the number of events. So then I can look at these individually and see like how many events were observed in each region. I can also look at for the signal Monte Carlo. This is part of the input to the ABCD method. And then I also need the total systematic uncertainty for the analysis. So this is a complicated number that I'm not going to worry about at all because it's the product of many dedicated studies and a real analysis. So I'm just going to say that for this artificial analysis, the systematic uncertainty was calculated to be 10%. So I just set it arbitrarily. So in this package, the main class is just this ABCD class. So this creates an object that carries information about a particular ABCD plane, which includes the yields from signal Monte Carlo and data, as well as this systematic uncertainty. So I pass in this information to make a new ABCD object. So I just import it and then create this object and call it ABCD. And so now I can use this object to do all of my statistical functions. So the lowest level thing that I can do with this object is just extracting the maximum likelihood estimators of the parameters that I was just talking about and their uncertainty based on the data that's been observed. So I can see all the parameters that are in this model by just doing this par names function. So mu is the parameter of interest, the signal strength. Then there's a systematic uncertainty, and then these nuisance parameters that I described earlier. And so I can do a couple different types of fits. So I can do a background only fit where I fix the signal strength to 0, and then it will return. So the first column here are the parameter values. The second column are the uncertainties in each parameter. It's just in the same order as they're listed by par names. And then I can also, so this is for the background only fit. So you can see mu is set to 0 here. And I can also do a fit allowing all the parameters to float so that the signal strength is set to its maximum likelihood estimator. So in this case, you can see the maximum likelihood estimator of the mu is like 12.8-ish. And so, yeah, I just explained that. So basically this is saying that the estimated mu is like 13 plus or minus 9, just going straight from the fit. Let's see. Okay, so I see there's a question on Slido. So from Nikolai, is there a reason for using this particular parameterization? For example, one can probably find a way that produces less correlations between the parameters. This is the standard way that the likelihood-based ABCD method is done in Atlas. So this was kind of set up by the Atlas Statistics Forum. There's certainly correlations between the parameters, but I haven't seen it cause any problems in the analyses that I've used it for. But there are certainly other ways to parameterize it. But this is the way that, at least the standard way to do it within Atlas. Okay, and I think Lucas's comment is or question is more of a comment about whether could some of these, well, okay, so if some of the inference driving stuff could use cabinetry, that is possible. That's something I haven't investigated, but yeah, it's possible. And yeah, exactly. This package adds to the models that are possible, that are kind of implemented without too much overhead in PyHF, because you can just use this package. Let's see, is there some assumption about signal uncertainty being the same across all regions? Yes, exactly. Yeah, that's a good question. And this is kind of an arbitrary thing. So the reason why it's set to a single number is because the analysis that I wrote this for is doing exactly that, using a single uncertainty for all, systematic uncertainty for all the 4 regions, but there's absolutely no reason why it has to be. And it's a very straightforward extension to make it so that it can be different in the different regions. And that's something that I plan to add. Yeah, it's certainly something that makes sense. It's just it was just the analysis that this was written for. Yeah, just used a single number. Okay, so I'll keep going. So next, you can extract the likelihood values at various parameter values. So there's a function that's just twice NLL. This is coming more or less directly from PyHF. It's just making this easy to run. So I can just do twice NLL. And then this will give me an array of, by default, it runs it at a variety of signal strengths. So that's what this first array is in here, all the signal strengths that it calculates, twice the negative log likelihood. That's what this is calculating. And then the second array is just the actual values of the twice the negative log likelihood. So these are the values. I can visualize this. I could plot it from that array there, or there's also just a function that's called twice NLL plot that just produces this plot. So here I can see that, okay, the negative log likelihood is minimized at this is the maximum likelihood estimator around 13. But a value of 0 certainly can't be excluded. This is, within a couple of sigma, certainly. I can actually say, I didn't put it in here, but the way that I generated this fake data was it's actually a background plus an injected signal with a strength around 6. So we can see that's the real underlying mu value is well within the uncertainty here. So there's really, I think, 6 signal events in region A. And then we can do so what are called CLS tests. So the values like CLB, CLS plus B, and CLS, these are values that are used, at least by the LHC experiments, for discovery and setting upper limits on signal strength. And so there's this reference here that's used for a lot of PyHF, and you can also see it for and mention some of how CLS is used if you're not familiar. So I won't try to describe the CLS method here, but just a note that you can get all of these values. So I can get the CLB values. So this is the same kind of format as the twice NLL. You get the mu values, the signal strengths, and then the corresponding CLB values. and then the same for the CLS plus B values. And then what we really generally care about the most for in terms of getting final analysis results in terms of discovery or setting upper limits on a particular signal is CLS. So if I run this CLS function, so again, I get all of the signal strengths array, then I get the observed CLS values, and then the expected band, which is the median value of CLS, assuming that the true value of mu is 0, and then that median value plus or minus 1 sigma, and also plus or minus 2 sigma. So it's a lot of numbers. It's easier to visualize in terms of what we often call a Brazil plot. So this is another function that's just implemented without having to put in all the parameters in the right places. It'll just automatically create this plot for you that shows, that scans across the different mu parameter of interest values, and then shows the observed CLS values, the expected CLS, and then the green is the plus or minus 1 sigma, and then the yellow is the plus or minus 2 sigma. And then in terms of the final results, so here we see that basically the observed values are within, in all cases, it's within the 2 sigma band, so we certainly wouldn't be able to claim any kind of discovery here. But so we would set upper limits on the signal strength. And so usually we'd be setting an upper limit at a 95% confidence level. And so that would be where these lines intersect 0.05. So that's this red line here. And then there's another function that just extracts those values. That's just called upper limit. So if I do upper limit, then I get the observed upper limit is the first number. So this is where the solid black line intersects the red. And then the expected upper limit band, which is where all the other lines intersect this red line. So the observed upper limit is like 30. The expected was closer to like 19.5. So we can see this upper limit is a little bit more than more than a 1 sigma deviation. So it's an indication that maybe there's signal there. And in this case, because it was set up in an artificial way, I know that there really is signal there. So if we collected more data, increased the statistics, eventually this would become significant. And at some point we'd discover the signal, hopefully. Okay, so that's kind of the end of just showing how this fairly simple little package works. So just in summary, the ABCD method is one of the simplest and most common data-driven background estimation methods. To be more pedantic, it's really a family of many methods that use very similar techniques. You can use more regions, you can arrange them in a more complicated way, but almost all of the methods that are actually used in modern analyses are some variant of the likelihood-based method described here. And so this package, ABCD PyHF, is a small pure Python package that only depends on NumPy, Matplotlib, PyHF. So there's no dependence on any experiment-specific formats or code, even though this was developed for an Atlas analysis originally, but it's all on GitHub, it's open source, it's public, and there's nothing Atlas specific about it. So basically for any experiment that is interested in using this kind of method, any analysis, this works out of the box for most simple cases, and it's intended to be extensible to accommodate more complicated cases. So if you have something that doesn't fit into the box that this package currently provides, then please let me know, contact me, or make a GitHub issue or something. I'm using this for my own Atlas analysis right now, and an early version of this was used for analysis that was already published. And there are a few other Atlas analyses now that are also using this, or at least trying out this package to see if it can simplify their workflow. And then I just added a few links at the bottom for the GitHub repository for the actual package. It's on PyPy. You can just do pip install ABCD PyHF. There's also an ACAT poster from last year. Let's see if there are any more questions. I see another one from Lucas. Is there some affordances in which these ABCD regions can be included into a larger likelihood? I think so. That's kind of what I was getting at when I said here about the extensibility. So I think I'm designing this in a way that I think it should be fairly straightforward to extend this to include more regions or part of a larger likelihood. But yeah, it's definitely something that I'm considering. There's another question. Is the interface extendable to higher dimensions? That's another. So it depends on exactly. If your regions, if you still have the same number of regions, you can use this no matter how many dimensions you're cutting in. But you probably mean like the more common scenario would probably be where you have more regions. And that's again something where I think the extension is fairly straightforward. It hasn't been implemented, but I've seen some analyses that would be interested in using something like this, but use more regions. So that's again something that I'm investigating and I think would hopefully be not too difficult.
Okay. Yeah, thanks a lot. Perfect on time. Currently, I don't see any other questions on Slido, but yeah, please feel free to continue the discussion on Slack. And yeah, thanks again for presenting this really nice package. I think it's really great to have these kind of commonly used methods in places also where one can figure out all the details. That simplifies really a lot of things and avoids mistakes that people could make